we are getting better at writing programs. We have languages, tools are getting better. We have higher level, strongly typed programming languages, better tools like debuggers. These keep getting better, except for the occasional backward step like C++. But they're not getting better fast enough. Corollary to Moore's Law, you've all heard of Moore's Law. Well, you may not realize the corollary, that not only does the size of the computer double, but the complexity of software doubles every 2 years. Actually, it's not quite that bad. In fact, every 3 years, because of software engineers aren't as good at doing things as hardware engineers. But we're still an exponential growth, and we're still falling further and further behind. The problem is that there's one tool that hasn't improved in the last 40 years, or perhaps the last 40,000. It's the one that's sitting on top of our spinal cords. We need to make better use of this tool. How can we? Well, there's actually a very simple way. Before writing a program, we should understand what it's supposed to do. This is self-evident, but it is surprisingly seldom obeyed. Programmers believe they understand what their program is supposed to do. But believing doesn't make it so. The best way to know if you really understand something is to write it down. It's one of my favorite quotes from the cartoonist Wyndham. Writing is nature's way of letting you know how sloppy your thinking is. If a programmer writes a description of what a program should do, it's usually vague and incomplete. And I say if because most often programmers don't write a description of what their programs do. But if a programmer does, it's usually vague and incomplete. And moreover, it's usually a description of what the entire program is supposed to do. And it doesn't, programs usually don't write descriptions of parts of their programs, individual methods or procedures, which means that they have no way of determining whether those pieces are going to work right when they're put together, except by building the whole system and seeing what it does. I don't see how you can if you delete something that's not there, so obviously the delete must be unsuccessful. On the other hand, after the operation is there, the object, file isn't there after you complete the operation, so that seems pretty successful attempt at deletion. So should it return true or false? Damned if I know. And damned if the implementers do either, because I believe that this does different things when executed on Unix or that it does when executed on Windows. And this or something like it, caused a program I wrote once to work on Windows, but to work on Unix, but not on Windows. Now it's fine to leave it unspecified, leave on what it should do in that case, but you should make clear, the writers of this specification should have made clear that if they where the unprimed variables refer to the value in the initial state, the first state, and the prime variables refer to the values in the new state. So the meaning of this is a relation between a relation between its initial and final state. It says that the value of x in the
final state is twice its value in the initial state, and its value of y in the final state is equal to its value of y in the initial state plus twice the value of x in the initial state. And we can make it look like real-life mathematics by using this, and now we have a genuine mathematical formula. Now, this may look pretty trivial. Actually, it's revolutionary. You ask people, what's the meaning of this program? Well, you say, well, it takes it, multiplies x by 2, and then it adds x to y. In other words, they think of it as a recipe. What Floyd taught us is a program, the meaning of a program is not a recipe. The meaning of a program is it's not a sequence of instructions. It's a relation, a simple mathematical object. It's static. Relation is a lot simpler than a recipe. Moreover, another important observation that Floyd made is that the meaning of the entire program can be deduced from the meanings of its components, the meanings of these two statements and the meaning of the semicolon. So we can reduce the problem of understanding a program to understanding its parts. And that's the key to handling complexity. The key to handling complexity is to break the whole into its parts and understand the parts separately. And then we can understand what they do when we put them together. So it's the key to handling complexity. So should this English description have been replaced by a mathematical formula? No. Our understanding starts with an informal idea of what the delete operation does. Just math anywhere in the documentation. And the implementers had no idea because it behaves differently on Windows than it does on Unix. So how do we avoid this kind of problem, where you have things that you couldn't even have thought of? And the answer is to use formal math. Formal math shows you how sloppy your math is. So what's formal math? Formal math is math done in a machine parsable language that has a precise formal semantics. We need it to be machine parsable. We need to have precise semantics in order to build tools. It needs to be machine parsable if we're going to build tools. It needs to be formally specified because it's not going to help us understand things if we don't understand what the language means. So what language should we use? Well, how about a nice, pretty graphical language? Here's a diagram. It's a UML diagram. UML is a Universal Modeling Language. And this diagram describes relations among a few classes of data items, or data objects. Now, these relations can be easily described expressed in simple formulas. For example, this part of the diagram says that, means that for every, you have a set of accounts and a set of customers, and for every account A, owner of A is a subset of the set of customers. This part of the diagram says that the cardinality, the number of elements in this set of owner of A, is either 0 or 1. Similarly, this says that for every customer C, accounts in C is a subset of the set of accounts, and this star means absolutely nothing. Well, what's wrong with these pictures? Well, one problem is that you need a new kind of arrow or a new keyword for each type of relation that you want to express. And that leads to dozens of constructs, dozens of arrows and stuff, just describing relations among classes. And there are lots of other things that you want to describe. The probably an even worse problem is that when things get complicated, pictures just become an incomprehensible mass of boxes and arrows. We went through this once, back in the 50s and early 60s. They had this wonderful pictorial language for describing programs. It was called flowcharts. We learned that they just don't work. When things get complicated, the flowchart just becomes an incomprehensible mass of spaghetti. So we learned to draw pictures in kindergarten, and you did not learn everything you need to know in kindergarten. So what kind of math should we use? Well, this UML diagram, incidentally, was I took from the lecture given by a UML expert. And in the course of trying to understand what was going on, I asked him to explain the meaning of a variant of that diagram. You know, what would happen if I changed this part of the diagram to something else? And he tried to explain it to me, but he wasn't able to. We exchanged, 2 or 3 emails, and I still couldn't understand what he was saying. So finally I said, look, stop using these words, just explain it in simple math. And here's what he said. He couldn't do it. He said, because asked him to do it in terms of just simple sets. So he said, set theory is static and does not involve notions such as namespaces and contexts. But it is hard, and it's not something that you're going to be using, in your professional life. And, among this many people, there's perhaps one of you in this room who someday, in the course of your work, may use a theorem prover, at most. It's not something that, in the next 20, 30 years is going to be very common. What I'm talking about are tools to execute your math. The way a program executes the way a computer executes your program. For those of you who know what it means, think model checking rather than theorem proving. If you don't know what it means, don't worry about it. So what I'd like to do is just give you a little example of how this works. A little example from graphs. A graph is a set of nodes together with a set of edges connecting the nodes, and I'm talking about undirected graphs. And the degree of a node is defined to be the number of edges that's incident on the node. So for example, here's a node that has degree 3. Now there's a nice little theorem from graph theory that says every finite graph has at least 2 nodes with the same degree. And so, for example, these 2 nodes both have degree 2. There are actually 2 nodes with degree 3 and 2 nodes with degree 1 in this graph as well. But the theorem says that there are 2 nodes with the same, at least 2 nodes with the same degree in any finite graph. And let's have a simple proof. Well, if there are 2 nodes with degree 0, then we're done. If there's 1 node with degree 0, let's remove it. So we now have n nodes, and let's suppose there are n nodes left. Since there are each n-1 other nodes that they can be connected to, the degree of each of those n nodes is a number from 1 to n-1. It's not 0 because of stuff. Okay, so in TLA Plus, specification is written as a module, so we'll call this module graph theory. So the first thing it does, the statement extends finite sets. That imports the definitions from another module called finite sets. This is a standard module that comes with TLA Plus that I wrote. Standard because I wrote it. It's easy enough to write. And it has a definition, it defines an operator that we need. Okay, let's define nodes to be let's pick some specific
fixed arbitrary set of nodes, call it nodes. This is going to be a parameter of the specification. So we assume some given set of nodes, which are the set of all possible nodes at the graph. So what's an edge? An edge is something that joins two nodes, and it's undirected. So we can represent the edge joining the nodes M and N as the set containing the elements M and N. So the set edges, which will define to be the set of all edges, is the set of all sets that form M comma N, such that M and N are elements of the set nodes. We're going to be using will have hundreds of processors inside of each chip, so they're going to be concurrent systems. And you can use the model checker to execute your descriptions, and it's fun. You know, it's just like programming. I've seen it happen. You know, it's work with engineers. Work with an engineer who, for some reason, gets